Welcome back to part 2 of this chapter. Now we shall continue the introduction of chapter 1 by giving you first of all the historical picture of the spectrum of ethanol as recorded in 1951. So different isotopes may have different spins. First of all, there are quite a few isotopes, such as the ubiquitous carbon-13, which makes up about 99% of organic matter, and oxygen-16, also all over the place, have no spin at all. Although they have a charged nucleus, of course, and of course the nucleus may well be spinning around, why should it not? It does not have a spin. And so the magnetic quantum number cannot be different from, can only be 0, and there's no transitions, and one cannot do any NMR at all. But this is a long series of important nuclei that have a spin 1/2 and that are actually very popular in NMR spectroscopy and also in imaging. Some nuclei, some isotopes have a spin quantum number equal to 1, mostly deuterium and nitrogen-14, also lithium-6. Some of them have a quantum number 3/2. Typical examples are boron-11, sodium-23, chlorine-35 and 37. By the way, sodium can be used in MRI as well. And then some have a spin 5/2, such as oxygen-17 and aluminum-27, which is actually very interesting to observe in aluminosilicates. And finally, some have a spin 3, and there are some exotic examples that go beyond. Not only do they have spin, but they have different gammas, different gyromagnetic ratios. So this is the gyromagnetic ratio. This is an inherent property of the different isotopes. And here you can see that they've been given in the proper units of inverse Tesla and inverse second. But that means that if you multiply with a field of 9.4 Tesla such that the proton NMR frequency appears at 400 megahertz, then automatically the deuterium NMR frequency appears at about 61 megahertz and the carbon-13 at about 100 megahertz. You should remember that there is a factor here of about 1/4, and you might also wish to remember that there's a factor of about 1/10 between the proton and the nitrogen-15 frequency. So these frequencies have been given appropriately in a field of B0 equal 9.4 Tesla, because that in fact is quite routine. In the current world of chemistry and physics, there are many spectrometers that operate at 400 megahertz because it's reasonably cheap and yet very effective. Now we also see that the natural abundance of these isotopes varies a great deal. For example, deuterium is only found 0.015% in ordinary seawater or in rainwater, so that's not very much, so you may wish to enrich it if you want to observe deuterium. Carbon-13 is about 1%. That can be observed directly, but of course you can boost it by enhancing the population or by labeling the molecules with carbon-13. Nitrogen-14 need not be boosted, but it's very difficult to observe because it has a very large quadrupole splitting. As you can see, nitrogen-14 has spin 1, and this is one of the things that we have worked on in Lausanne over the last few years. Nitrogen-15 is very popular in biomolecules because you can introduce it synthetically by cloning techniques into molecules, in proteins in particular. O17 is still challenging. Fluoride-19 is very popular because it has a very high abundance, 100%, and also because one can find fluorine-19 in many drug molecules, but not in natural living matter. Silicon-29 is popular for those studying silicates and aluminosilicates, and phosphorus is very popular in biochemistry because there are many important phosphates moving around in organisms. So you see, every isotope has a characteristic spin quantum number. Now there's some rules about these quantum numbers, and for example, if the number of protons and the number of neutrons are both even, then the resulting spin quantum number is 0. That is the case for carbon-12 and for oxygen-16. But you can also have the case where both the protons and neutrons appear in odd numbers. Then we have integer numbers, quantum numbers, such as 1, 2, or 3. They could be even and odd, or odd and even, and in either case we have so-called half-integer spins. Actually, these rules are not particularly useful. It is better to look at a full table like here. Now, the electromagnetic spectrum is very vast. It ranges from very high frequencies and very short wavelengths to very low frequencies and very long wavelengths. So in spectroscopy, it is the gamma rays that are used in Nussbauer spectroscopy that have the highest energies, higher than X-ray, and X-rays again are more energetic than ultraviolet and visible, and then we have the infrared range, and below that the microwave range, and at much lower yet we have the radio frequency range. So this has several consequences. First of all, the radio frequencies are largely innocuous. Nobody really worries that when you listen to a transistor radio on the beach that you might get irradiated by the transmitters or by the receivers. So radio frequency is quite innocuous, and that has great advantages for MRI. Radio frequency is also can penetrate through all sorts of tissues, including living humans. Again, you can check with your radio that it works even if you lie on top of it, and that is the reason why MRI is so popular, whereas with doing imaging of humans with visible light is of course very difficult. Now, NMR actually also had other advantages, and that we have a great spread of frequencies, and here on a scale where 400 megahertz would correspond to protons, you see the fluorine-19 is in the vicinity, phosphorus-31 is somewhat below, and then the ubiquitous carbon-13 appears at about 100 megahertz. But even if we have a high-resolution spectrometer that can resolve different chemical shifts, then one can distinguish various types of protons. So, for example, at the top end we have the aldehydic protons, and at the bottom end aliphatic protons. 0 actually corresponds by convention to tetramethylsilane, and all of this range spans about 4 kilohertz out of 400 megahertz, which corresponds to 10 ppm, and indeed that is the common scale used here. So the frequencies of NMR transitions are typically in the range between 10 and 1000 megahertz. Incidentally, the world's most powerful machine is indeed 1000 megahertz of protons, and you can find it at Lyon in France. Now we shall consider a nucleus with a magnetic moment mu, so this is a magnetic moment, immersed in a magnetic field B. We can arrange this magnetic field so that it's parallel to the z-axis, or if you prefer, we can just align the z-axis of our coordinate system with the field. In that case, all we have to worry about is the product of the z component of the magnetic moment and the amplitude of the field. It turns out that this z component is determined by the product of m, that's the magnetic quantum number, h bar, that's Planck's constant divided by 2 pi, gamma, the gyromagnetic ratio, and the amplitude of the field. Remember that this m here can be plus or minus 1/2 if I equal 1/2. So if I equal 1/2, it follows that m is either plus or minus 1/2. Now the splitting in energy can be described as simply h bar times the absolute value of gamma times b, and the NMR frequency is the same as the splitting divided by h bar, by h, so that we have simply this divided by 2 pi. Now for a spin 1/2, as I said, we have either m equal plus 1/2, and we call this the alpha level, or we have m equal minus 1/2, and we call this the beta level, and we have a single transition. So this is the case for a spin 1/2. But if we have a spin 1, such as for a deuteron or also for a nitrogen-14, then we have 3 possibilities. We have m either minus 1 or 0 or plus 1, and indeed we have 3 different levels. It turns out that the obvious nomenclature alpha, beta, gamma is not common in our business, so we just use these quantum numbers. And we notice that if this spin, it could be a deuteron, a deuterium, or a nitrogen-14, is dissolved in an isotropic liquid, then in fact it turns out that the energy splitting between the top and middle level is exactly the same as the energy splitting between the middle and bottom level. So these two transitions are degenerate. So when we see a line like this, it actually half of it comes from the top transition and half from the bottom transition. Whereas in this case, for protons, for example, there is really only one transition. So let's attempt to summarize the main points of the introductory chapter. First of all, every isotope in the periodic table has a characteristic spin quantum number I. Some isotopes have I equals 0, in which case it is just impossible to do NMR. This is the case for carbon-12, and the only way to rescue the situation is by replacing the carbon-12 with the carbon-13. Now, every isotope with I different from 0 has a characteristic magnetic moment mu. Nuclear spins have 2I plus 1 distinct energy levels, and these energy levels are labeled by magnetic quantum numbers, lowercase m, which can vary from -I to +I in steps of 1. In a magnetic field, the energy levels are split by an amount that is proportional to the size of the nuclear magnetic moment and to the strength of the magnetic field. So NMR spectroscopy uses electromagnetic radiation to induce transitions between energy levels. The frequencies of NMR transitions are typically in the range between 10 and 1000 megahertz. The intensities of NMR signals depend on the differences in the populations of the energy levels. These populations are determined by Boltzmann's law, and by the temperature, and by the field, and by the gyromagnetic ratio, and all of these parameters conspire to make NMR a rather insensitive technique, and this is in fact the Achilles heel of NMR, is that one often needs very concentrated samples or very long experimental times to get decent signals, sufficient information, and this is one of the driving problems why so many NMR spectroscopists are trying to improve the methods. Thank you.